For those of you who are not familiar with JTS, we manufacture custom condensing units, chillers, and refrigeration racks. Typical applications are anywhere from 5 horsepower to about 500 horsepower. We really live in that gray area in between commercial and industrial. I'm the head engineer over there. I've been at JTS for about 7 years, but I've been in the industry for going on 20 years. There's a couple of you in here that I've known my entire career, which is pretty awesome. Anyhow, we're here to talk to you guys about a refrigerant glide and how it affects refrigeration systems. So it's kind of exciting times that we're living in right now. We're kind of on a third wave of refrigeration revolution. So kind of the first wave was like in the 1920s and 30s when they developed R12 and R22. That got phased out in the late 80s and 90s with the Montreal Protocol and the ozone depletion and all that. And that brought on the second wave, which was blended refrigerants. That included like your R410As, your 404As, that sort of thing. We're in the midst right now of a third revolution, which is kind of phasing out these refrigerants due to their global warming potential with newer blends. They consist mostly of a bunch of A2L refrigerants. We're also seeing a big transition to natural refrigerants like CO2 and ammonia. Seem to be getting bigger. All right, so blended refrigerants, they were initially created in response to phase-outs. Refrigerant manufacturers develop new refrigerants with varying component concentrations to obtain the perfect balance. Perfect refrigerant has low toxicity, is low inflammability, environmentally friendly, energy efficient, and it has great application flexibility. Blends offer advantages over single component refrigerants in the sense that you can get improved thermodynamic efficiency, they reduce the environmental impact, and enhance safety. Most blended refrigerants have glide. So let's talk about some of the cocktails on the menu. We got I'm going to start with a real familiar one here, R410A. It consists of 50% R32, which is an A2L refrigerant. That's mixed with 50% of R125, which is a fire suppressant. Yes, sir?
Can you just a little closer to the mic?
Yeah, you betcha. Thank you. All right, so 410A consists of 50% R32, which is a mildly flammable refrigerant. It's being mixed with 50% R125, which is a fire suppressant. You mix these two parts together, you get a non-flammable refrigerant. Likewise, R507 is mixed with 50% R125, which is your fire suppressant, and 50% R143, which is a flammable refrigerant. Again, when you're mixing the two parts, you get a non-flammable refrigerant. Some of the newer refrigerants that are coming out include R454C and R454B. These both consist of 2 parts of A2L refrigerants. So both of them consist of R32 and a mixture of R1234YF. However, they exist in different component concentrations. So for instance, R454C has about 21% R32, whereas R454B has about 69% R32. All 4 of these are 2-part blends. They're known as binary blends. You also got trinary blends, which include R404A and R455A as an example. So R404A is very similar to R507A, except for it's got about a 4% R134A component. R455A is very similar to R454C, except for it's got a 3% CO2 component. And then you got your multi-part blends. These are your R448A and R449. 448A consists of 5 different refrigerants. There's a lot of parts going into it.
Right? Can you repeat that? Are they used as A2Ls or no?
What's that?
A2Ls.
A2Ls?
Are they equal?
Yeah, so R32 is an H-well.
Yeah, but when you make it really,
Yeah, when you make the blend, they don't consider it A2L.
Oh, yeah, yeah.
If you're mixing, like 410A, for instance, is an A1 refrigerant, because it's mixed A2L with a fire suppressant component.
Is the fire suppressant component still in the refrigerant?
It is, yeah. R125. All right, so we're here to talk about glide. Basically, there are two parts to any blended refrigerant, two types. There's what we call an azeotrope, or I've heard it pronounced a few ways: azeotrope, azeotropic. I'm not 100% sure which is right, but an azeotropic refrigerant, they consist of R507, R513A, any R500 series refrigerant. These are blends that behave like a single component. So as you move across the pressure enthalpy diagram, you've got a constant temperature and constant pressure. The term azeotropic is actually Greek in origin. Ace is Greek for no, zeo is Greek for boil, and tropic is Greek for turning or change. Therefore, an azeotropic is a refrigerant that does not change temperature as it boils. On the other hand, you got zeotropic refrigerants. Zeotropic refrigerants change temperature within the heat exchangers. This change in temperature is known as glide. All your 400 series, including 404A, 410A, 454B, 454C, any 400 series refrigerant is considered a zeotropic refrigerant. Zeotropic refrigerants can be distilled into their individual components, whereas azeotropic refrigerants cannot. The easiest way to understand glide is to understand vapor quality. So vapor quality is the amount of vapor that's present in the mixture of liquid and vapor mixture inside your heat exchangers. And I'll get into it a little more here, but with azeotropic refrigerants, if you got 100% liquid, 25% vapor, 75% vapor, or 100% vapor, your temperature stays the same. You have 0 degrees of glide. Azeotropic refrigerants have constant temperature within the heat exchanger. R404A and your zeotropic refrigerants, for instance, they change temperature as that liquid boils. So R404A at 80 psi with 100% liquid is going to have a temperature of 35.9. If you got 100% vapor, saturated vapor, your temperature would be 36.8. Difference in these temperatures is your glide, which in this case is 0.9 degrees. To understand glide, we got to understand the pressure enthalpy diagram. So I'm going to go over that real quick. Over here on this scale, on your Y scale, you got pressure. On your X scale, you got enthalpy. This curve is known as your saturation dome. And everything underneath this curve is a mixture of liquid and vapor. Anything to the left side of this curve is known as saturated liquid, subcooled liquid. Anything right on the edge of the curve is known as saturated liquid, or is your bubble point. Up here at the very top of the curve, you got your critical point. With blended refrigerants, we're typically operating below the critical point. Anything to the right of the curve, you have superheated vapor. And right at this edge of the curve, the right edge, you have your saturated vapor, your dew point, or what's often referred to as your saturated suction temperature will fall along this edge. Down here are those vapor qualities that I was talking about. So at this far edge over here, you've got a vapor quality of 0. That means it's 100% liquid. On this line going up, you've got a vapor quality of 0.1, which means that you've got 10% vapor and 90% liquid. If we go over to this side, you've got a vapor quality of 0.9, which is 90% vapor, 10% liquid. And if you go to this far right side, it's a vapor quality of 1, indicating that you have 100% saturated vapor. No liquid. So oftentimes the refrigeration cycle is mapped out. A couple guys have already gone over this, and to save time, I think I'll skip this section. But we are going to look at the individual components of what's actually happening. So right now, we're going to look at the condenser. So as discharge gas enters a condenser, you got this first leg over here on the far right. This is known as the superheating. So what it's doing is it's stripping heat out of the vapor, but we haven't yet condensed. Once you cool the temperature to a point where we hit the saturation curve, you hit the dew point for the refrigerant, and that's where we have a 100% saturated vapor. As that refrigerant travels through the condenser coil, in this case, we're actually changing temperature as our liquid becomes more and more concentration in the coil. If you notice at the end of the coil, at the end of the vapor curve at the bubble point, we've got a very different temperature than at the dew point. In this case, with our 455A at 257 psi, our dew point is 117 degrees, our bubble point is 100 degrees, and our mean temperature is about 108 degrees. So your mean temperature would be your average or midpoint temperature. Our 455A in this application has about 17.3 degrees of glide. Pretty substantial. So what actually happens inside of a condenser coil? What we got here is it's kind of a plot to help understand. You got, on this axis you have temperature, and then on this axis you've got heat exchanger thickness. So what happens in most condenser coils is you get counterflow heat transfer, where air is entering at a lower temperature and you're heating that air up as it passes through the coil. Refrigerant is entering at the opposite end of the coil and traveling through. If you've got an azeotropic condenser, an azeotropic gas, then your dew point and your bubble point are the same temperature. So therefore, there's not a change in temperature as that refrigerant goes through the condenser. Your condenser has a delta T that's usually measured from the entering air temp to historically we've used the dew point, even though the dew point and the bubble point are the same on an azeotropic refrigerant. Now if we look at a zeotropic condenser, you have the same thing occurring where within the heat exchanger you got cooler air that's being heated up. Now with a zeotropic refrigerant, our dew point is going to be higher than our bubble point because the refrigerant is going to change temperature as it goes through the condenser. You notice here our dew point delta T is larger than our midpoint delta T. So due to this, kind of what it means is it means that most condenser coils, when you're using high glide refrigerants, they have a smaller delta T to the median temperature of the refrigerant. That basically means that you need larger heat exchanger surface to reject the same amount of BTUs. So next, let's talk about what happens going through the expansion valve. Based upon your condensing temperature and the amount of liquid subcooling, your liquid line would then enter the expansion valve, which expands the refrigerant. As it expands the refrigerant, we start generating a mixture of liquid and vapor. What enters the evaporator coil is very dependent upon where you're condensing and what your liquid temperature is before condensing. But generally speaking, you're entering at a vapor quality somewhere between 0.25 and 0.5, so somewhere in this area. Based upon whatever your vapor quality is, determines the temperature of the refrigerant at the very inlet of the evaporator. So in this example, it might be 15 degrees at very first pass of the evaporator coil. Now, as that refrigerant passes through the evaporator coil, it's going to pick up heat, it's going to evaporate refrigerant, And as it does so, our vapor quality is going to increase until we get to the very edge of the saturation curve. At this point, we've got a 30-degree dew point. The last pass or two of the evaporator, you're actually generating a little bit of superheat. So in this example, our 455A evaporating at 53 psi has approximately 15 degrees F entering the evaporator, approximately 30 degrees F dew point, and our evaporator mean temperature difference is kind of the middle point in between this point and your dew point. So to illustrate the same basic function that's happening inside of evaporator, again, we're going to plot the temperature versus the heat exchanger thickness. Evaporators are similar to condensers in the sense that they usually have counterflow heat transfer. With a traditional azeotropic refrigerant, your refrigerant inlet temperature to your dew point stays about the same temperature. You don't have a change in temperature as that refrigerant boils. However, you're cooling the air from a warmer temperature to a lower temperature. With a zeotropic refrigerant, you still need the dew point delta T. This is necessary for any evaporator in order to generate superheat. However, because your refrigerant has glide, your mean temperature delta T is larger. Therefore, one thing that's common is your evaporators typically gain efficiency when you're using high glide refrigerants. So to kind of map out both the condenser and the evaporator, the amount of glide that's generated through each is very much dependent upon the change of enthalpy. A condenser will always condense from a dew point to the bubble point. It travels all the way across the vapor dome. Your evaporator only travels partially across the vapor dome. It's very much specific, related to what your liquid temperature is and what your condensing temperature is. So your change in enthalpy through the evaporator, again, it could be anywhere from an evaporator vapor quality of 0.25 to 0.5. But something else that's interesting here, if you look at these lines going across, these are your lines of constant temperature. They're at a constant slope. Some other things that affect this, like different refrigerants have different shaped domes. This particular one, R455A, it's kind of pitched a little bit to the right. Others of them are more straight up and down. Some of them are a little taller and skinnier. Some of them are wider. So the change in enthalpy is very much different depending on what gas you're using. But the concept remains the same. So kind of as indicated here, your heat exchangers are often sized based upon a mean temperature difference. Compressors and other components are often sized based upon dew temperature. In this example here, I got a couple of Bitzer compressors pulled up. The first example is R455A. We're referencing dew point. The 30-degree saturated suction temperature, 117.3 dew point condensing temp. So it's telling us that we need a condenser capacity of 200,000 BTUs per hour. So if we went to our condenser supplier and said, hey, we need a condenser that does 200,000 BTUs per hour at 117.3 degree condensing temp. You have to be very aware of how that condenser coil rates their condensers. If they come back to you with a selection and then they say, here's your 117 degree condensing temp. Oh, by the way, we rated this at midpoint. All of a sudden your condenser is not properly sized. If they come back in, if the condenser supplier rates their condensers based upon mid temperature or midpoint median, you need the equivalent of 108.6 degree condensing temp. So there's a pretty big difference between 117.3 and 108.6. It would be, approximately half the glide of that condenser coil that you'd be shorted in the condenser selection. So system designers need to ensure that you always reference the same temperature, or you can compensate by adding temperature to the compressor selection. Calculating superheat on glide refrigerant is pretty much the same as what we're used to. The biggest difference is that you have to reference dew point. As mentioned, refrigerant will increase in temperature the closer you get to the dew point. And what you're trying to measure is you're trying to measure superheat that's generated beyond the dew zone. So in this example here, we've got a 67 psi measured on your suction outlet, and we got 54 degrees at your pipe temperature. If we use our favorite converter tool or a gauge, you can convert a 67 psi to approximately 40 degrees, and you can deduct 54 from 40 to calculate your 14 degree superheat. One thing that's interesting about this is with R455A. If we look at what's happening inside the evaporator coil, we got liquid feeding into a metering device. Coming out of that metering device, we might have 25% vapor quality. That means this first pass of the evaporator coil is going to be 26.3 degrees. As that refrigerant travels through the heat exchanger, we're going to boil off more of the refrigerant, and our temperature increases as our vapor quality increases. At this last pass over here, we finally hit our dew point of 40 degrees, which is a vapor quality of 1. Everything past here is just generating superheat. So the difference between 40 and 54 is our 14 degrees of superheat in this case. One thing that's interesting to note, 26 degrees on an evaporator coil is pretty cold, especially if you've got, maybe this is a 60 degree air temperature application. It's possible that the amount of glide may cause frosting to happen on air heat exchangers at an earlier, warmer temperature. It's also possible in liquid chiller applications that you may need more antifreeze to protect against freezing. If we look at calculating subcooling, again, it's pretty standard compared to what we're used to. The biggest difference is that you have to reference the bubble point. So again, on our pressure enthalpy curve, we're looking at the amount of liquid temperature coming off the condenser coil that's left of the condenser curve. So in this case, we've measured a discharge pressure of 206 psi, which converts to 84 degree liquid temperature. And then we're measuring the liquid temperature coming out of the condenser coil, which is 74 degree liquid temp in this case. So 84 minus 74 is 10 degrees of subcooling. But if you'll notice what happens as that refrigerant travels through the condenser coil, we are actually decreasing in temperature as our vapor quality decreases. Fractionation. Has anybody heard that you got to charge with liquid when you're using blended refrigerants? Yeah? Alright, so you gotta, the reason that they recommend this is because fractionation happens within the charging bottle. So the fractionation potential is determined upon the component pressures, right? So if we look at R455A, it consists of about 3% CO2, 21.5% R32, and 75.5% R1234YF. So at 80 degrees, the CO2 component has a pressure of 955 psi. The R32 component has a pressure of 232 psi. And the R1234YF component has a pressure of 89 psi. The difference in pressure between these is great. Therefore, one would expect that this refrigerant would have a very high glide and very high fractionation potential. R404A, on the other hand, is considered a low glide refrigerant. It consists of 44% R125, 52% R143, 4% R134A. If we look at the pressures at 80 degrees, for these refrigerants, they're much closer together. You'll notice that the R125 and the R143 are almost the same pressure. And these are the biggest components to that refrigerant.
Question on that for a moment. So like,
Yes, sir.
let's say I'm gonna take out the field,
Right.
and I have to kind of add additional charge, and I don't have a transfer pump, so it would be difficult for me to charge with a liquid. If I have to add, say, 5, 10 pounds to a 100-pound system, I'm probably gonna charge through the suction line as a vapor. How critical is that?
Yeah, so that's kind of what this next, what this image right here is showing. So if you've got a low fractionation potential refrigerant, that is, parts A and B are close to the same pressure, and you pull, the liquid inside that tank is going to be exactly 50% mixture of each. That's why they recommend charging with liquid, because you're going to pull in the same percentage of each. If you pull off the vapor side of that tank, you're going to pull in 55% of the slightly higher pressure refrigerant, and you're going to pull in 45% of the slightly lower pressure refrigerant. Now, if the refrigerant that you're using happens to have high glide, that gets amplified. So you're going to, with a high glide refrigerant, you're going to end up pulling 80% of component A into the system and 20% of component B. So, if you're charging with vapor, it probably doesn't matter if you plan on using the whole container. It's all going to end up in the system and get mixed together. But honestly, if you're going to put a whole container into the system, it's a lot quicker to do it with liquid. So,
Johnson,
yes, sir.
so if you have a bottle of R455A,
Right.
they're all in the same enclosure. Obviously, they can't exist with different pressures in the same enclosure. So do you have a temperature gradient in the bottle?
Yeah, exactly. So what I believe is happening is there's a lot of interaction between the different molecules inside the bottle. And I think it's kind of almost creating like a little thermal cycle. But
It has to, right?
yeah, I mean the other thing is this is assuming that your bottle is sitting stationary. If you were to mix that bottle up, it all stays in solution. So while the system's running, you're not gonna have this effect. It mostly happens inside your charging bottle because it's just sitting there stationary. All right, so leaks can also cause fractionation. If you happen to have a leak on a refrigeration system, the location of the leak could determine how much fractionation occurs. If the leak is on a vapor line, it's unlikely to leak one specific component. It's likely to leak both. If your leak happens to be in a location where both liquid and vapor phases exist, it's highly likely that you're going to leak the higher pressure component. So leaks on heat exchangers, leaks on your liquid line, leaks in the vapor space near liquid receivers, highly susceptible to fractionation. Another thing to consider is leakage amount. So low leakage amounts are unlikely to cause a noticeable difference. Let's say you lose 10% of your refrigerant charge, you come back and you top it off with 10% new virgin refrigerant. You're not going to change the composition that much. High leakage amounts, again, are very similar. Say you lose 90% of your charge, and you come back and you top the system off with 90% virgin refrigerant, your composition, again, is still pretty close to what the refrigerant manufacturer originally designed. Worst case scenario is about a 50% leak rate. So if you leak out half the charge, you come back and you top it off with another half the charge, your composition is going to end up being a little different. One thing you can do an equilibrium PT check. This requires calibrated sensors. But if during the off cycle, you can compare your liquid line temperature and pressure to what you actually measure. If the two are substantially different, you might have fractionated refrigerant. It's pretty hard to measure within, to accurately measure within 5 degrees and even within 5 psi. So generally speaking, I would recommend sending sample analysis to lab for component verification of what's in your refrigerant if you happen to have a leak and want to reuse your refrigerant. Here's a pretty neat study that I found. It was done by Purdue University. They focused on R448A and they studied the fractionation effects of leaks. So here's a link to that study if anybody was interested. I'd recommend you research it. But basically what they did is they leaked out 20% of the refrigerant and they recharged with 20% virgin refrigerant and they repeated it a second time, 20% leak, recharged 20%, and they leaked it a third time and then they recharged it a third time. This red line down here is kind of their simulation of what they thought would happen. This blue line represents an experimental data of what actually happened. So what I think is pretty interesting here is at the start, here are components of R448A. It consists of 26% R32, 26.1% R125, 20.9% R134A, 20% R1234YF, and 6.9% R1234ZEE. After the third cycle, if we compare this column over here to the original, basically you can see that we went from 26% R32 to about 24% R32. So our higher pressure component was leaked out, and we've got about 2% less percentage of R32 after the third leak and recharge. If we look at our middle components, they're roughly unchanged. They're pretty close to the same. There wasn't a large amount of leakage on those. And if we look at our lowest pressure component, the R1234ZEE, it actually gained about 2%. I don't know if it actually gained it or if it's just an observed gain. Well, it would be gaining it as you add more refrigerant. You're actually changing the composition, so it gained a certain percentage of the lower component refrigerant. So I'm going to switch gears on you guys a little bit and talk about this third wave that's coming through of refrigeration. According to the EPA, starting in January 1st, 2026, we got some changes coming. Most chillers and air conditioners will have to be using refrigerants that have a GWP of 700 or less. Process refrigeration, if you're using more than 200 pounds of refrigerant, you have to have a refrigerant with GWP of 150 or less. If you have less than 200 pounds of refrigerant, you need a refrigerant with a GWP of 300. So here's kind of a list of refrigerants and what we see as being future refrigerants coming up. The first section of this list is your R507, 404A, 410A, R134A, and R448A. These are refrigerants that we've used for the last decade or two. You'll notice that your 507A, it's an azeotropic refrigerant, 0 degrees of glide. It's got a GWP of almost 4,000. It's an A1 refrigerant. 404A and 410A, they're low glide refrigerants, less than a degree of glide. Again, pretty high GWP. They're on the chop block. 448A, it's probably the one that we've used the most in the last 5 or 6 years. It's got about 8 degrees of glide. 1273 GWP, it's an A1 refrigerant. Where we're seeing the transition in chillers and air conditioners, we're seeing a lot of movement moving over towards R32, which is an A2L refrigerant. It's a pure refrigerant, so it doesn't have any glide. GWP of 677, so it's below that 700 GWP limit. R513A, it's a 500 series refrigerant, which means it's azeotrope. 0 degrees of glide, 573 is its GWP. It's an A1 refrigerant, which is pretty cool, non-flammable. R454B is actually where JTS is looking at. We're working with UL to get a UL listing on our chillers at the moment for R454B. It's got about 2 degrees of glide, 466 GWP, and it's an A2L refrigerant. For a lot of commercial refrigeration, you're gonna see a big movement to these two numbers, refrigerants, the R454C and R455A. Each of these have substantial amount of glides. You'll see R454C is about 12 degrees of glide on the condenser, and on the evaporator we're about 10 degrees of glide. Both of these have a GWP under 150, so they'll be allowed in 2026. They're both A2L refrigerants. Traveling a little further down this list, you got the R1234YF. It's actually what the automotive industry has switched over to. And then at the very bottom here, we've got our natural refrigerants. So JTS, and I know a lot of other manufacturers are looking into propane, CO2, and ammonia. So it's getting to be about lunchtime. Yeah?
What's happening in the residential market?
I think that you're going to see a lot of R32, like GWP of about 700 or less, I think is what you're going to see. And you're going to see R32 and probably R454B. Of course, every manufacturer is different, you know. So it's getting to be about lunchtime. I got a little food for thought inferencing study here for you guys. All right, so if we look at R454C, it consists of about 21% R32 and about 79% R1234YF. Now let's compare that to R455A. R455A is very similar, except for it's got a 3% CO2 component and 3% less R1234YF. So what do you think is going to happen to R455A if we have repeat leaks out in the field? There's a pretty good chance that it's going to start acting more like 454C. You're going to lose your CO2 component, and you're going to gain higher percentages of your R1234YF component. So if it starts acting more like 454C, there's some changes that happen. Due to this 3% CO2 component, R454A has significant more glide. It's got 18 degrees of condenser glide versus R454C, which has 12.5 degrees of condenser glide. So as you have repeat leaks, you're actually going to see a little bit less glide, which is going to maybe make your condensers a little more efficient, but it's going to make your evaporators a little less efficient, right? Another big thing is due to this 3% CO2 component, it makes R455A substantially less flammable. So the lower flammability limit of R455A is 0.231 pounds per cubic feet. The lower flammability limit of R454C is 0.0183 pounds per cubic foot. So if you're designing it, it's kind of a scary thought. If you design a system to have a lower flammability limit for this less flammable refrigerant, but after so many leaks, that refrigerant is probably going to become more and more flammable. Another thing that you'll notice is our saturated suction pressures. Our pressures are going to be a little bit lower. So if we look at a 35 degree suction temp, 10 degrees of superheat with R455A, that's a 59.56 psi. With R454C, the equivalent pressure is about 55 psi. So
I think there was a question.
Oh, yeah.
I would think that R32 having a higher partial pressure, you'd leak it, therefore your flammability would go down.
Yeah, so
Repeated.
I think you're leaking the CO2 component.
Oh, the R32 is the CO2.
No, the 744 is your CO2 component.
Okay.
So as this component leaks off and gets smaller, you're gonna look more like R454C.
Okay. So which one is the more flammable component?
So R32 and R1234YF are both A2L refrigerants. They're both
Oh,
mildly
okay.
flammable. But they've added this CO2 component to make it less flammable.
Gotcha.
And the consequences are, by adding it, it's increased the amount of glide of the refrigerant, but it's made the refrigerant substantially less flammable.
Yep, I see now it's the CO2 is going.
Right. Where I was getting at is basically your system, your suction pressure is going to end up operating at about 5 psi less. If your 455A does convert into more like your 454C, you're going to be operating at about 5 psi less suction pressure. But now your electronic expansion valve might not know that, right? So it's going to think that you have 13 degrees of superheat when you really only have 10. So it's going to start opening up if your set point's at 10, and ultimately you're going to end up operating the system with less than designed superheat. So, in summary, understanding refrigerant glide will help designers design better system and equip technicians the knowledge they need to work on the system. Glide is simply the change in temperature within the heat exchanger as the refrigerant condenses or evaporates. Heat exchangers are often sized on mean temperature difference. Ensure that the system design references the same temperature or is compensated for glide. Larger than traditional condensers are needed because smaller than traditional temperature difference. Smaller than traditional evaporators are needed because larger than traditional mean temperature differences. Air evaporators may frost at warmer temperatures. Glycol chillers may need higher concentrations of antifreeze. Only charge with blended refrigerants. Calculate superheat based upon dew point. Calculate subcooling based upon bubble point. And then it's recommended to have lab sample analysis of your refrigerant after multiple leaks, or to reclaim and recharge with virgin refrigerant. Questions?
Quick question for you.
Yes, sir.
So you guys you have like a product line for the A2Ls currently?
Yeah, we do.
What are you guys doing as far as like leak mitigation? Because you guys have to detect there's a leak.
Yeah, so most of our products are outdoor products. A particular product is a chiller, air-cooled liquid chiller.
Yep.
And so it's an outdoor application, and UL really doesn't have any limits on that.
Right.
Now, if we were to install that chiller indoors, all of a sudden, leak detection and exhalation valves, stuff like that come into play.
Okay.
Same thing with your condensing units. If the condensing unit is located outside, generally you're not required to have leak detection. I mean, there's enough free airflow outside that you're not gonna generate enough to hit the lower flammability limit of. But the connected system on the inside, you might have to have a mitigation like a leak detection, ventilation fans. ASHRAE 15 has great standards on how to design that. UL 60335-2-89 is another good one to reference.
Do you know if you if you have an evaporator failure and you get refrigerant mixed into your glycol circuit, is UL making you guys measure your refrigerant mix within your glycol circuit?
No.
Okay.
But yeah, we are working with UL at the moment. We've actually got a UL listed 1995 CO2 chiller coming out. We also got a A2L listed chiller coming out. Both are about halfway through the UL process. Questions?
Thanks, gentlemen.
All right.
And